We are live. Good evening. Let's do a little bit of biochem rapid review. Biochem is notoriously difficult. And the thing is, when I was flipping through the notes to kind of look for the topics that I wanted to do for this, it's really interesting. You can't touch on a specific part of biochem without going down a really deep rabbit hole, right? Because every part of this science kind of leads into one another. Like if you want to explain protein folding, you have to know a lot about intermolecular interactions, a lot about thermodynamics. You have to know a lot about the way that proteins sort of fold down themselves, all of amino acids, everything. You need to know all of that, right? So the thing is that you can't really touch upon things in short detail. So last week when we did our bio rapid review, it was like 10 topics in 2 hours, right? Here it might be more like 4 or 5 because we're really going to have to flesh out everything, all right? Okay. So first, how does my hair look? Because it's been giving me a lot of shit all week. Yeah, it will be gone soon. The next time you see me on camera, I might be here on Thursday. I have to let you guys know. It depends how my test goes on Thursday morning. If it goes poorly, I'm going to go home and cry. And I won't see you on Thursday. But I will email you guys Thursday afternoon-ish, which is fine because the lecture's at like 7 now. And if you guys want to show up. And I'll see you then. So, and then the next time you see me will be February the 20th, and I'll be bald. Okay, so let's first talk about proteins. We were talking a little bit about amino acids before, right? Let's talk about proteins and protein structures. So who can tell me what the primary structure of a protein is?
Isn't it just a list of amino acids?
Right, so it's just an amino acid after an amino acid after an amino acid after an amino acid. What sorts of questions can they ask you about the primary sequence or the primary structure of a protein? It's only really one kind, right? They're going to give you a string of letters and ask you about a specific portion of the protein. So what's a string of letters they give? They give you G, L, A, T, P, F, W, V, K, G. This doesn't look like much to someone who hasn't taken biochem before. But for my people who have taken biochem or are studying for the MCAT, can you please decrypt this for me? Everyone. So what's the first one? First one's glycine, then leucine, alanine. These are the ones, see? All right, threonine, right? Threonine stole T from who? It should have belonged to either tryptophan or tyrosine. Okay, then? Phenylalanine. No, sorry, proline. Phenylalanine's, see? Again. So phenylalanine is F, proline is P. F is phenylalanine. W, tryptophan. V, valine. Lysine and glycine. Very cool. All right. Now, here is the question they can ask. Let's say that this is an important protein for blood clot formation, right? And this is how the MCAT gets you. That's how they get you, right? So they're going to give you these two, and they're going to ask you, hey, are they fucked? Not really, right? Not really. They're not really fucked. Because what? We went from valine how do you do valine? Valine, right? To how do you do alanine? Doesn't make that much of a difference. They're both nonpolar. They're both what? What's the word for nonpolar in biochem? Aliphatic, right? Aliphatic, right? Which is weird because they're not fat. They're quite skinny, actually. And no, they're not fucked. They're going to be completely fine, probably. Maybe a little bit of like steric hindrance over there. What is steric hindrance again? Steric hindrance is when you have really, really large groups and branches and chains and things like that inhibit the motion of things around it because you know that nonpolar things attract nonpolar things and nonpolar things repel polar things, blah, 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 right? So Are they screwed? Probably not. Right. But then, yeah.
I have a question about that.
Yep.
So, in sickle cell anemia, something is switched to a valent.
I think it's G6V. I think. It's either that or it's no, sorry. It's D6V. Or V6D, something like that. So what happens is that I can just look it up. Because I should know it. I think I have to, like, before I look at it, I think it's either G6V or V6G. Sorry. My bad. It becomes a valine, so I think it's a glutamate that becomes a valine, D6V or V6D. Okay, so let's look up SCA mutation. It is. I remember looking this up. Yeah, it's D6V. Nope. E6V. There we go. I was wrong every single time I said it. Okay, so sickle cell anemia is a mutation of glutamic acid to valine on the 6th position of the protein. Right? What was your question?
So my question is, the reason the valine is a problem is because it causes this stacking, which makes these fibers that spike out of the hemoglobin. So if you have
It doesn't explode.
excuse my terminology.
Yeah. So what happens is the blood cell, right? This is an important protein, and that specific position is important for the way that the protein forms. And what happens is that you get the blood cell to sickle, and it no longer carries oxygen properly, number one. And number two, this sickled blood cell isn't good at moving through capillaries. So it will clog up really, really, really small vessels, especially in the kidneys, and it can cause kidney failure. So going off of that, the rest of your question.
So my question is, could you have a situation over there where the valine does matter because of this stacking?
It probably wouldn't. That's the thing. Like why I asked you, are they fucked? Probably not. Right? Probably not. It might, right? If this was like the most important part of the active site of the enzyme, maybe. But the assumption here in the MCAT knowledge that you kind of need is like nonpolar. So I'm going to give you an example in a second to clarify exactly what they would want from you, and we're going to take a look at what a question could look like. Yeah, Sarah?
Is what you said about aliphatic?
Yeah.
I thought that was like single bond versus like
So aliphatic is nonpolar, non-aromatic. Aromatic kind of already implies a little bit of nonpolarity, but there are obviously polar aromatic compounds. Aliphatic just means nonpolar, non-aromatic, because when we have aromatic amino acids, we call them aromatic, right? Also, know the difference between the terms aliphatic, amphiprotic, amphoteric. You can look those up. Because we're going to talk about what they could ask you about this. So here's the question they could ask you. And this is a question that kind of gets under the skin of a lot of MCAT students, right? Kind of pisses people off. So you have a string like that. Which of those is the worst? This is how the MCAT pisses you off. We'll get there. So first, let's identify where the problem is, right? So GAKLWPFF, there we go. All right. Then, where's the next one? GAKLWPFFT, there we go. Where's the next one? GA, there we go. Right? And then here, there we go. So T, so this is T for S. This is D for E. This is K for E. Sorry, I didn't underline that. And this is R for H. And now who can identify all of those amino acids and their subclass? Laura.
So T to S, threonine to serine.
Yep.
They're both
They're both what? So this is threonine.
I mean, they're both polar.
This is threonine, right? And this is serine. Not much of a difference. They're both polar, so that's not that bad. Right. What about D for E? Anyone else? Aspartate to glutamate. It's one carbon difference. They're both carboxylic acids. Not that big of a difference. K for E. Hold on.
It's lysine for glutamic acid.
Yep. So lysine
It's a positive to a negative, which is a
for
glutamic acid.
glutamic acid. I believe it's 2 carbons, correct? Yeah. That's a big problem. That's a huge problem. R for H. Anyone? Arginine for histidine. They're both positive, right? And when we say positive, do we mean basic or acidic? Basic. We mean basic, right? Okay. So that's how the MCAT pisses me off. And probably pisses you off too. What's up? Yeah, they would also ask for charge, which is really annoying. Especially if like they don't say it's a full protein, they just give you like a short peptide because they want you to know that like some of the answer choices, like they're gonna say at this specific pH, right? And the pH may be low enough or high enough for the C terminus or N terminus to be positive, negative, deprotoned, whatever it is. Because normally the C terminus, N terminus, they cancel out to be 0. Right. I don't know if you guys watch the YouTube videos ever, like just for review, stuff like that. The microphone makes like the biggest fucking difference in the world. I was watching part of the lecture just to test the audio, like when I put the microphone down. It was the part where I was talking about pi stacking. I put the microphone over here and my voice is just like completely different. And then it's almost like, you know, like putting on noise canceling headphones, like I bring the microphone back and my voice is just clear as day. It is crazy. And what's wild is like they're literally this small. It's unbelievable. I love these things. Not sponsored at all, but Rode Wireless Go-Tos if you guys ever want to record stuff. You know, if you guys are like the people that bring tripods to the gym and record like straight up your asshole while you're doing squats. Fucking ridiculous, man. This one person I went to high school with, like became this huge gym influencer, blah, 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 whatever. Dude is like maxed out on steroids. He's like 22 years old. Probably murdered his testicles. I was like, bro, like, please, relax. Oh, man. Okay, so that was primary structure out of the way. Secondary structure. Who can tell me the most important fact to know about secondary structure? There's obviously a few, but what's the most important thing to know? Hydrogen bonding. Right, is that what you were going to say?
No, I was actually not.
What were you going to say?
I was going to say that, actually no, I was going to say something about.
So hydrogen bonding is the important component of secondary structures, right? Because there are 2 different structures inside of secondary structure. They are known as the alpha helices and beta pleated sheets. Alpha helices and beta pleated sheets. So when these form, they form off of the interaction of hydrogen bonds, right, within the protein molecule. So let's say you have one part of the protein, like let's say we're making a beta sheet, right? You have one part of the protein that's like, I think I actually have to draw it, right? And then and how do you know you're drawing it properly? Your heads are going to go opposite ways, right? Every other head is going to be pointed the opposite way. Now, this is one part of the protein, and then it's going to turn and turn and turn. And at another part of the protein, you're going to have what? And this is going to line up in such a way that a hydrogen bond forms between the carbonyl of the amide on a partial part of the molecule, on another part of the molecule, or the other way around, that the H over here might form a hydrogen bond that way with the electrons of that nitrogen. Right. Now, who can tell me A, B, right? This is A, the bond between the nitrogen, the hydrogen, and B. What do we call A and what do we call B? A is a hydrogen bond blank, and B is a hydrogen bond blank.
The NH thing is the hydrogen bond donor, the O is the hydrogen bond acceptor.
Yeah, so donor and the electrons specifically. The electrons of the oxygen are the acceptor. It's an exchange that's going on, right? Are hydrogen bonds actual bonds? No. They're really, really, really strong intermolecular or intramolecular interactions. Good? Okay. What's one specific thing? Probably not going to come up on the MCAT as a discrete problem, but you might get a passage about it. Who can tell me my favorite thing to talk about beta pleated sheets? Prion disease. Prion disease. All right. So there is a prion disease known as, the most common, Creutzfeldt-Jakob disease. Creutzfeldt-Jakob disease. It's basically a variant of mad cow disease, right? So what happens is that you have a protein inside your body that is PRPC. And if you ingest or come into contact with a protein that is misfolded PRPSC, this is the prion form. And that prion form can go and turn other normal proteins into prion proteins, right? And those can accumulate inside the brain and cause dementia. So that is a rapidly progressing dementia. When you see that in like a question stem, like I'm taking my neuro exam in 2 days, when you see that in a question stem, it's like some young person, no reason for them to have dementia, 48, 50, maybe even late 30s years old. Rapidly progressing, forgot how to do their daily tasks of life over the past 2 weeks, doesn't recognize people, blah, blah, blah. And like they have a bunch of behavioral changes. That's the big thing, because this classically causes a frontal dementia quickly. Like it more rapidly happens inside the frontal lobe. Also, this is different than frontotemporal dementia, also known as Pick's disease, right? But that's probably Creutzfeldt-Jakob disease if it happens that fast. That will unfortunately kill you. Like there's really nothing we can do about that. Yeah.
You get mad cow disease if you eat something that's infected. How do you get Creutzfeldt-Jakob?
I don't know. You come into contact maybe through like a biopsy specimen, infected blood, like something like that. I don't exactly know. Sometimes like I think you could just get unlucky.
Really?
I think the protein could just
Not the answer.
the protein could just misfold. I mean, you could okay. Here's the thing. When I tell people, well, we can figure out right now. Actually, you know what? We'll do one better. This is first aid. Okay. Creutzfeldt-Jakob disease. Rapidly progressive with dementia with myoclonus, or like it's just a muscle problem. And ataxia, associated with periodic sharp waves on EEG, increased 14-3-3 protein CSF, may be transmitted by contaminated materials. For example, corneal transplants, neurosurgical equipment. So unless you're getting a transplant or someone's fucking around inside your brain, I don't think you're going to get Creutzfeldt-Jakob disease.
Okay, I'm feeling better. Thank you.
It is 100% fatal. It will kill you. And yeah, that's about it. So do not worry about prion disease. The thing is, like a lot of people, when I tell them about these diseases and everything, and obviously it happens when you're in medical school as well, a little bit of, phobia, a little bit of, fear. I forgot what that's called. To be afraid of hypochondriac. Yeah. Being a little bit of a hypochondriac, right? Why? Like, is it any more scary than getting hit by a car randomly while you're walking to school? Like, no, probably not. 1 in 3 people, like everyone quotes this statistic. Oh my God, 1 in 3 people in their lives develop cancer. What kind of cancer? Treatable, not treatable, curable, not curable, metastatic, malignant versus, benign. Like, yeah, a lot of people develop skin cancer over the course of their lives, but a lot of skin cancer is treatable. If it's not melanoma, it's pretty treatable. Like basal cell carcinoma, pretty treatable, right? So it's just like, whenever you encounter scary statistics, and whenever you encounter scary information about something, do a little bit of research, do a little bit of background, right? Don't let things scare you right off the rip. You're not going to get Creutzfeldt-Jakob disease. You'll be fine.
If he was worried, you're like, oh, you could just get on the
I mean, you could get it. Like, how do you think the first person got it? They got unlucky. How did the first person get cancer? Got unlucky. How do you get Down syndrome? You get unlucky.
That's why you can't, some people are cannibals. That's why you can't eat a human brain.
You cannot eat a human. Do not eat human brains. So what are the do nots of this? Don't huff acetone. What's another do not? Don't kill yourself. Don't kill me. And don't eat human brains. Yes. Don't do that. Do that. And I don't know. I'm running away from you when I go. All right. So that's secondary structure, right? Tertiary structure, right, is interaction. We know this. This is like quoted all the time. Interaction between the R groups, right? So hydrophobic, hydrophilic interactions, right? And the quaternary structures bring together a bunch of tertiary structures. Now, the important next step in understanding how proteins work and everything like that is asking yourself, right? Asking yourself the thermodynamics of protein folding, right? And there's one specific thing that's always quoted in the thermodynamics of protein folding. What is that one fact? Yeah, so the entropy is what's important, right? The entropy is what drives the force. Because we say that delta G equals delta H minus T delta S. And we say that protein folding is a delta G negative process. But we say that that's because of the delta S. The delta S of what? The protein or the water surrounding it, right? So when proteins fold, let's say that we have a protein like this. Let's say we have a protein like this. And these are the R groups sticking out like this. Some of these R groups are polar and will be very easily solubilized. But let's say this is a specific part of the protein on the interior before it folds. It's supposed to go on the interior, right? And it's on the exterior right now. What's surrounding it in the cell? Water, right? And the water is going to need to create a little barrier around all of these polar R groups and restrain itself around that in order for those R groups to not interact with anything else. Because if it does, you're going to die, right? So, also, sorry, back on prions for a second, because I said you're going to die. The beta-pleated sheets, right? The beta-pleated sheets, prions basically are just beta-pleated sheets. They're misfolded proteins that have beta-pleated sheets in them. They encounter other proteins that are scrambled up like this, and then that causes the other protein to just unfold and misfold like this. And then they conglomerate and they deposit like that. Yes?
I read somewhere, I think in Oxford, that they started off as an alpha helix. Is that true?
I don't know. I have no idea. All right, so back to this. The water surrounds all these little R groups, protects them, almost like my cells, right? Because remember GI, right? When we were talking about GI physiology, we ingest little lipid molecules and we tag them onto one another. And what happens is that we turn into phospholipids, whatever it is. And a phospholipid bilayer is going to surround the entire glob of fat and cholesterol and fat-soluble vitamins, et cetera, and that's going to get transported out into the blood like that so that it doesn't interrupt anything else, right? So the same thing's happening here. Now, when the protein starts folding and these R groups start to kind of kiss, right, they interact with one another and nothing's allowed in between them, all of that water that was bound up is now able to leave. So the water becomes free when the R groups start interacting with one another, right? So the water no longer needs to babysit this. That causes a drastic increase in entropy of the water. That entropy drives the reaction. Good? Okay. Would anyone like to comment on that any further? Moving on. You guys are going to hate me for this one. You guys are really going to hate me for this one. Because I hate myself for this one. you already don't like it? Yeah. All right. And obviously I have the answer right here because, you know. All right. So this is what? A double reciprocal plot. This is also known as a Lineweaver-Burke plot, right, of enzyme kinetics. And right here, what is this value right here? Negative 1 over Km. You can shout out answers, I don't mind. What is this? 1 over Vmax. Very good. Okay. So, I'm going to ask you a series of questions with dotted lines. Who can tell me? Who can tell me what that is? With confidence. A competitive inhibitor. So this is a competitive inhibitor. All right. So what happens in a competitive inhibitor? Your negative 1 over Km, and I'm going to say I right here, goes up? Interesting. Well, if negative 1 over Km, let's use some numbers. Let's say it was negative 2, right? And it becomes negative 1. Well, that means that negative Km equals 2, and here it means that negative Km equals 1, which means that Km equals negative 2, and Km equals, did I do that right? Oops, sorry, 1/2. There you go. And then here, I knew I was doing something wrong. And then here, Km equals negative 1. Right? So the thing is, sorry, let's do that again. I messed myself up. Negative 1 over Km here is negative 2, and here is negative 1. So negative 1 over Km is negative 2 over 1. Let's do it like that. And then negative 1 over Km I inhibited is negative 1 over 1. Let's get rid of the negative. So 1 over Km equals 2 over 1. And then 1 over Km equals 1 over 1. Which means Km is 1/2 in the original, and Kmi is 1. What do we want, a lower Km or a higher Km? We want a lower Km. Lower Km is better. So the inhibitor is making the Km worse. How? Yes?
So the inhibitor is competitive, so it's blocking up the active site. You're going to need more to occupy half of your active site to keep together.
Yeah, so the definition of Km is the level of substrate that occupies half of the active sites. What are you doing all the way back there? That's not your spot. Come. I know you can't read from back there. Come forward. So the Km goes up, You need more substrate in order to occupy the same number of active sites. Now, can this type of inhibition be overcome? How? Pump full of fucking substrate, right? Because that's the same thing that we were talking about before, where, do you guys remember when we were talking about like SN1 reactions, where the leaving group comes off and the leaving group has electrons on it? So for a second, let's just talk about that, because this is kind of important. So the leaving group comes off, and then when we have the attachment of the solvent molecule, right, we ask ourselves, what's going to deprotonate that? Now, the question is, it's always the water, right? It's always the water. Why isn't it the Br? Because there's so little of it in contrast to the water, the solvent, because the solvent is always added in such huge excess. So the way to overcome competitive inhibition, let's say that this is your enzyme, this globe-looking thing, and this is the active site right here, and you have little circles that fit inside of it, right? And the inhibitor is this oval guy, right? If you want to overcome the inhibition, just throw so many more of these in there, because the chances are, the probability is that the enzyme is going to interact with that instead of the inhibitor, right? The inhibitor. A lot of drugs, a lot of drugs are competitive inhibitors of specific enzymes. Cool. So what's next? What's the next natural step after competitive inhibition? All right, let's take a look. I love how excited you guys are for non-competitive inhibition. So if we're fucking with the Km in competitive inhibition, what are we fucking with now? The Vmax, right. So both of our graphs are going to come off of the same -1 over Km, right? So we got one like this, and we got one like this. Notice how I didn't dot one of them, because I want you to tell me which one is the inhibited one. Graph A or graph B? Knowing, take everyone, take a second, think about what's on this axis from the example I just gave you, and tell me which one is the inhibited plot. Everyone. A, yeah? Okay, why? Because what's on these points? 1 over Vmax. And what are we doing if we're inhibiting? We're taking Vmax and we're putting it down. And if we go down, 1 over will go up. So this is 1 over Vmax I. This is your inhibited plot. What does a non-competitive inhibitor bind? An allosteric site, right? So here's your enzyme. This enzyme is in charge of making me feel depressed, right? Working overtime these days. And here's your allosteric site. And this little guy comes and goes right there and inhibits the enzyme, decreases its velocity, right? Sarah, do you have a question? Can it be overcome? Not really. No. Because, unless you put more enzyme in, right? But that solves everything. Putting more enzyme in solves absolutely everything. All right, so those are the two big ones you're going to see all the time. All the time. Let's talk about, and then obviously, uncompetitive inhibition. What is uncompetitive inhibition? Uncompetitive inhibition is interesting. And it's one I never truly understood until after I took the MCAT. I started teaching it because I had to encounter this over and over and over again because so many students had questions about it. So let's say that we have, I hate that I started with substrate. Enzyme substrate turns into enzyme substrate complex, turns into enzyme and product. Right. Okay. An uncompetitive inhibitor binds where? It binds right here. And the majority of Km is based on what? So the ES is going to be turned into ESI. Km is based on what?
It's the KM is based on how much you need to occupy half of the enzyme to occupy active sites.
Right.
It's a measure of efficiency.
Right. But that's kind of the definition, right? And we talked about that before, but let's ask a higher level question. What exactly influences the Km in this specific example? Because I'm going to tell you something. The Km in this example, who knows what happens to the Km? It goes down. Really, really interesting for an inhibitor to cause the Km to improve. Why?
It gets stuck in there for longer, so it has a stronger affinity, so the KM.
Okay, Malcolm. All right. Anyone else? Any other thoughts?
The substrate can still bind to the enzyme. It's just afterward you can't release a product.
Right. So here's the thing. We're measuring, when we say half of the enzyme's active sites, we're measuring the disappearance. Because it's not going to disappear unless the substrate binds. And if it gets caught up in ESI, the concentration of ES falls, and more of it binds, and more ES forms, and more of it gets lost, and blah, blah, blah. So when you don't have disappearance, when you don't have reformation of free enzyme, the Michaelis-Menten in his grave is just like, holy shit, look at this. Absolutely fantastic, amazing binding, no unbinding, right? So that's really, really good for the Km. But it's also really bad for the Vmax. Because the Km and the Vmax, they're not communicating with one another. They're not talking. He doesn't know what's going on here, and he doesn't know what's going on here. This dude's having a fucking rave. This guy's on ecstasy right now, right? This guy is getting nothing because all of the substrate is tied up in an an untransformable position. You can't move forward from there. There's no E plus P from ESI. There's only E plus P from ES. So if you get tied up like this, no product. No product. Now, what could the plot possibly look like? Because the thing is, they don't really give you a plot for this because it's good. The thing is, there's no real plot for this because it could depend on how much the Km changes. But let's say, for example, you have a plot like this, and here's your negative 1 over Km. Your Km goes down, right? Which means it's going to shift more to the left. And your Vmax goes down, which means it's going to shift to what? Up. I'm going to fix that. If you ever see parallel lines on a Lineweaver-Burke plot, that's uncompetitive inhibition. How are you going to remember that? These two lines, they're not competing for space. Uncompetitive. Not non-competitive, uncompetitive. Also just like uncompetitive. Yeah.
And the shorter line is the inhibitor.
Yeah, sorry. This is the I.
The one on top or
On the top. Vmax goes down, which means that 1 over Vmax goes up. If 1 over 2 versus 1 over 3, this is 1 over Vmax. This is 1 over Vmax, which means Vmax here is 2 and Vmax here is 3. So velocity goes down, 1 over Vmax goes up because 1/2 is greater than 1/3. Confusing algebra. I hate it. I had a buddy in undergrad. What's your major? Pure mathematics. Oh, God. How? I'm no better. I'm really no better. What's your major? I think all day. I think all day and try really hard not to kill myself. was a good one. I like that. What is suicide inhibition? Irreversible inhibition, right? So basically, you got an enzyme. This is the active site. Some molecule comes in, and the enzyme just loves it so much, it covalently binds the enzyme. Shut down, absolutely not. Nothing else is allowed. It's like a cage, right? And the only way to get rid of this is to break down and reform more enzyme. Who knows my favorite example of a suicide inhibitor?
Is it aspirin or those NSAIDs?
So yeah, aspirin is an irreversible inhibitor of cyclooxygenase. That's a very, very good example. I actually don't know if it's a suicide inhibitor or not, but okay, so let's rephrase the question because I don't know what type of inhibitor it is. What's my favorite example to bring up when I'm talking about inhibitors in general? I brought it up twice, I think, during the lecture. Yes, but there's one that's very interesting. It's very relevant to history. Sarin gas. Nerve gas. Sarin gas is an acetylcholine esterase inhibitor. And when you inhale it, it inhibits acetylcholine esterase, which is the enzyme that breaks down acetylcholine. So when your body releases acetylcholine onto the diaphragm in order for it to contract and expand your chest cavity to get in air, if you inhibit acetylcholine esterase, you don't break down the acetylcholine that's hitting the diaphragm stays contracted and you can't breathe out. And you choke to death on your own breath.
We don't have to know the line for birth plot.
The Lineweaver-Burke plot, like, rumor has it, it just has blood, like, splattered all over it. Some dude tried to figure it out. He's dead. He, like, FBI broke down his door, hung him right there. Michaelis came back out of the grave. Shot the guy in the back of the head. Did a little nay-nay and left. All right. Who knows the difference between an epimer and an anomer?
Epimers they have a bunch of chiral centers and they're different at only one chiral center.
Before you talk about anomers, anyone else? Who knows what an anomer is? I like to write it out like this. Because it's an alpha-beta thing. Anomer, right? Anomers are the difference between alpha and beta sugars. Who knows the difference between alpha-beta sugar? Not you. Anyone else? Do you know? What's the difference between alpha and beta sugar?
In the cyclic form, the OH on the alpha one is pointing down, on beta is pointing up.
If it's a D. If it's a D sugar. Yeah, so what's a D? So then we need to know what's a D sugar, right? So in a cyclic form, when it's a D sugar, this little group is pointing up, right? And now we need to compare the anomeric carbon, the OH on the anomeric carbon, which used to be what? This carbon used to be the aldehyde, right? The anomeric carbon. If it's going down, this is alpha. We also call that trans, right? Because, right? And then beta, cis, right? Bis. Binsulin. Binsulin and glucagon. Right? Those are anomers, right? Most common epimer question on the MCAT. What is the C4 epimer of glucose? Galactose. The C4 epimer of glucose is galactose. So David, Come up here for a second. Here is a backbone for a D sugar. And here is a backbone. Well, I guess D sugar, right? Okay. Here I want you to write glucose. And here I want you to write galactose. You can do the little trick, yeah. Talk me through it.
So for the glucose, you flip the board. The finger pointing that way means OH is going to be here, H is going to be here, OH pointing here, here, here. The left one, the last one is the wrist. For galactose, C4 means this one. 1, 2, 3, 4 is going to be reverse. It's going to be here. This one still is the same. Same. This one's going to be here. This one's going to be here. This one's going to be here. And this one's going to be here.
Very good. Now cyclize both of them.
Oh my god.
Glucose you should know off the top of your head.
Yep. OH is going to be here. Glucose should point down here, up here, down here. That's glucose and galactose. This guy's here, this guy goes down. We have still pointing down, pointing up, pointing up, pointing down.
All right.
Readable?
I'm checking. So glucose, right? So
Down.
if it's the C4 epimer in the straight chain form, it's also going to be the C4 epimer in the what? Ring,
Mm-hmm.
right? So identify the 6 carbon for me on glucose. On glucose.
1, 2, 3, 4.
Right. So if it's a C4 epimer, it's going to be flipped on what position?
On
The 4
this.
position.
Yep.
Right, so fix your drawing. Not glucose. Glucose is correct.
Oh. Here.
Fix your galactose, right?
Yeah.
So that's going to go up, which means, where's your mistake? Your 2 position,
2 position.
right? Because your anomeric carbon is carbon 1.
Yeah.
It used to be the aldehyde, right? Perfect. Now, one last question. Actually, that might not be as important. I think that galactose is a beta 1,4 bond, or it's either an alpha or a beta 1,4 bond between glucose and galactose. Just identify, if they were to bond 1,4, right? Identify the 1 carbon and the 4 carbon on both of those rings.
And if that's the 1,
That's the 1 carbon.
that's the
That's
4,
the 4 carbon. Beautiful.
that's beta. Yeah. It's going to be.
Perfect. Good. Wonderful. Now you'll never forget it.
Hold the power.
Thank you. The power. The power of the microphone. Yeah. So 1, 2, 3, 4. And here's the thing. The reason I want you to do that is because sometimes they're not going to give it to you like this. They might give you this, right? And you can't go off of the 1 carbon because it's anomeric. It could be up or down. You're going to have to look at the rest of these and compare them to your mental image or draw an image in front of you when you take the exam of glucose. And you're going to be able to identify that this is the 1, 2, 3, 4 C4 epimer of glucose, right? Because that's the opposite one right there, right? Okay, very good. So you can recognize, even in a ring, that this is galactose. Okay. Do I recommend you memorize all of the epimers of glucose? No. Maybe it'll help you get a 528. I certainly didn't want one. I knew I wasn't going to get one. I got close enough. You got close enough for me to be happy. Highest score I've ever heard of is a 526. I know someone who got a 526. Fucking beast. He's an ophthalmology resident right now. Okay. Okay. Who can tell me the irreversible steps of glycolysis? Laura? Joseph? PFK is one of them. Another one? Pyruvate kinase is one of them. And there's one more, hexokinase, right? So we got 3 people, 3 steps. Can you draw one of them for me? With structure. Okay, fine. Then dictate me through it. So let's talk about number 1. Well, what order they come in? So we said 3 irreversible steps. The first one, obviously, hexokinase, right? Let's do hexokinase. Let's do a little arrow, right? What is turning into what? Very good. Okay, so glucose is turning into glucose 6-phosphate. Very good. Very good. Using what? Is a kinase enzyme. It uses ATP. ATP. Number 1, irreversible step of glycolysis. The second irreversible step of glycolysis was PFK1. And it's also what? The rate limiting step, right? Everything in glycolysis is contingent upon the pace at which this step happens. So the glucose 6-phosphate turns into fructose 6-phosphate using what enzyme? Phosphoglucose isomerase, right? Fructose 6-phosphate turns into all right, so PFK1 is going to take ATP because phosphofructokinase and turn fructose 6-phosphate into fructose 1,6-bisphosphate. Why bis? I actually used to know. I forgot. Well, no, but why not biphosphate? Why bisphosphate?
I think it's the same exact thing like we did the first time.
Yeah, I forgot.
Can I ask you a question?
Yeah, what's up?
For the flashcard, it says that the PFK1 is inhibited by ATP, but doesn't it use ATP to become glucose 1,6-phosphate?
Let's talk about, remind me of that in like literally 2 seconds when we finish that last step. That's such a good question. That's such a fantastic question. Number 3, what's the final step?
That's the pyruvate kinase.
Right.
You get rid of an ATP.
You do.
Yeah, you give it back to ATP.
Can anyone fill in the rest of this structure? What we start with? Well, who knows what we start with? What do we start with in this step? PEP. Phosphoenol pyruvate, right? How do you draw the rest of it? So you drew a line. There's a double bond somewhere, right? And then what else? There's a phosphate. How did you know it goes this way? Because it's an enol. It's supposed to be an enol, right? If that was an OH, that'd be an enol. Right. And this is pyruvate kinase, which gives you back an ATP, as was so expertly said. Now, Joseph had a fantastic question. PFK1 is actually inhibited by ATP. Right? And that's what the mile down says. That's what the Anki says. And if the Anki says it, it's word. And that is correct. It is inhibited by ATP, but it uses ATP. So what gives? there's a difference between enzymatic ATP and cellular ATP. What they mean by inhibited by ATP is that what? More properly, more appropriately, it is inhibited by a high ATP to ADP ratio within the cell. A high energy status of the cell will inhibit PFK1 because that means there's enough energy that's been made. And that means we don't need to push forward to glycolysis. And that means that G6P builds up and G6P gets shunted towards no, G6P gets shunted towards glycogen. Glycogen. You can start making glycogen. Right. Good? Okay. What's a potent activator of PFK1? What is the biggest activator of PFK1?
Maybe ADP?
Kind of. The biggest activator. No. You have to know it. The MCAT's going to fuck you if you don't. They want you to know this. I want you to know this. I'm going to start crying if someone doesn't say it right now. What is the heaviest activator of PFK1?
PFK2.
Technically. What does PFK2 make? If PFK1 makes fructose 1,6-bisphosphate, PFK2 makes fructose 2,6-bisphosphate. Okay. So the heaviest activator is fructose 2,6-bisphosphate, which is created from the activity of PFK2, which is part of the bifunctional enzyme in the liver, which is PFK2 and what other enzyme? FBPase2. So this side is what? This side is insulin dependent. And this side is glucagon dependent. Because insulin's going to push forward glycolysis, and glucagon's going to push it back.
What does this bump say?
PFK2 and FBPase2. FBPase2 being fructose 2,6-bisphosphatase. Why did we talk about the irreversible steps of glycolysis? Because I lied to you. And everyone lied to you. And the entire world lied to you. And you should never trust anyone ever in life ever. Because these are reversible. Just not by the enzymes that you see in front of you. So, can anyone tell me what the enzymes are that we use to reverse these reactions? This is tough. This is tough. Basically what we're asking, this is glycolysis. I'm asking you, what are the key enzymes in gluconeogenesis? So the first one's probably the easiest one, right? How do you go back? Glucose 6-phosphatase, right. And watch this, guys. Everyone look at the board. Oh shit! Look at that! Glucose 6-phosphatase. Ready for another one? Watch this. Oh man, look at that. What's the next enzyme? PFK1, and then if fructose 2,6-bisphosphatase did the breakdown of, fructose 2,6-bisphosphatase is the breakdown of fructose 2,6-bisphosphate, what is this? FBPase? 1. Fructose 1,6-bisphosphatase. Which is the rate-limiting enzyme of? No. Gluconeogenesis. Is this a one-step reversal? No, it's not a one-step reversal. And it's the enzymes that everyone forgets. Everyone forgets these enzymes. What are they? Okay, so we have pyruvate carboxylase. What's the middle? Who's in the middle? Oxaloacetate, right. So let's draw that guy in. 1, 2, 3. I think, no. Is that it? I think that's oxaloacetate, right? Let me check.
Letters for like OOA,
OAA.
OAA,
OAA structure. This is, I'm missing one carbon. I knew it. I knew it. Oxaloacetate. Yeah. And then back to PEP would take what? PEP carboxykinase. What are the cofactors for those? I have to look myself because I haven't been over this in a while. Yeah?
Can you please go through the enzymes one more time because there are a lot of abbreviations?
Yeah, sure. I'll do it once we're done with this. So first, the first thing is when you do a carboxylate, obviously you need to carboxylate it with something, so you use CO2. And the other thing is gluconeogenesis requires an energy input. So you need ATP. But that ATP doesn't get incorporated. It turns into ADP and PI. And then this step needs ATP that does get incorporated. And then that's how you get around that. Okay, so hexokinase to turn glucose into glucose 6-phosphate. To go back, you need glucose 6-phosphatase. PFK1 to turn fructose 6-phosphate into fructose 1,6-bisphosphate. Fructose 1,6-bisphosphatase to go back. And then here, PEP to pyruvate needs pyruvate kinase, which is named after the reverse reaction for some reason, right? And to turn pyruvate back into PEP, you need pyruvate carboxylase, which uses the hydrolysis of ATP to carboxylate itself, and then, or to carboxylate pyruvate. And then you need PEP carboxykinase, or PEP-CK, to go back to PEP from OAA. Very, 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 very good. Okay? Yeah? What time is it? Jesus. Oh my God. Time flies when you're not having fun. Well, you guys aren't having fun. I'm having a blast. What is this? It's fatty acid. Yeah.
I'm sorry, you just noticed it. So for the reverse of K, you use 2 molecules of ATP?
You do.
And if it's for reaction, only use 1 molecule?
Use one. Gluconeogenesis requires an energy input. This is a fatty acid, right? How do we get energy from this? Right, beta oxidation. So we're going to take this. We're going to turn it into fatty acyl CoA. Thank you, guys.
Have a safe trip.
Thank you, man. Appreciate it. Fatty acyl CoA. And then we're going to oxidize with what? We're going to oxidize with FAD first. And that's going to turn this into that. And then we're going to add water. And that's going to turn that into that. And then we're going to oxidize with. Also, this isn't the main part of the lesson, so if you're copying this down rigorously, don't bother. We're going to oxidize with NAD because NAD does heterooxidations. And that turns that into that. And then eventually we turn this into this and that, right? And now we made acetyl-CoA, NADH, and FADH2. And that acetyl-CoA is going to go into the TCA cycle and turn into 2 CO2, 1 GTP, and how many NADH and FADH2? 3 and 1. You round this guy up, and 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 where do they go? They go where? They go to the electron transport chain. So that's how we use fatty acids as a store of energy. So that was the main point of this part of the lesson. And now, let's cry a little bit. We go over to the electron transport chain. How many complexes in the electron transport chain? Really? Technically 5, because ATP synthase is sometimes called complex 5. But I never call it complex 5. I think that's stupid. But it's just like an MCAT fun fact. Which complex is celibate? 2. Complex 2 is celibate. No pumping. No premarital pumping. All right. Complex 1 is what? NADH Q oxidoreductase. NADH and its associated proton are going to come, not that type of come, drop off their electrons here and drop them off onto what? They're going to drop them off onto the textbook, and biochemists like to say iron sulfur cores, right? Basically, little things that are made up of iron, sulfur, whatever, FMN, all that stuff. And basically, they're just going to travel up this little oxidation ladder until they get to Q, and they're going to turn Q into QH2. So the overall reaction is this. What is the general structure of Q and QH2? Q would be this, and QH2 would be that. A quinone and a hydroxyquinone. Oh, by the way, Q and QH2. Just go back 5 seconds. Okay, complex 1, pumps. H plus into the what? Into the what? Intermembrane space. Remember, we're in the mitochondria right now. Does anyone remember, like, trivia Jeopardy question about the MCAT, right? Here's the mitochondria, here's that. Here's the electron transport chain right here. Does anyone remember the pH difference between the intermembrane space and the matrix? It is very different, but what's the pH difference? 1. The pH difference is 1, which means, here's the next question, how many times higher is the H plus concentration here than here? 10 times higher, right? If you have an H plus concentration of like 0.5 here, you have a H plus concentration of 5 here. Next. Complex 2. Complex 2 is a square. Why? Because he gets no bitches, no pumping, right? What's the thing here? The complex 2 is actually closely associated with an enzyme. What enzyme is that? Succinate dehydrogenase. Because the succinate dehydrogenase has the FAD on it, and then the FAD turns into FADH2 because it turns what? It turns succinate into How fucking cool is that drawing? And then the FADH2 drops its electrons off onto FMN, blah, 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 whatever, whatever. Eventually onto Q to QH2. No pumping. You're a cowboy. You lasso up all of your QH2s and you bring them over where? To complex 3. Complex 3 is that really, really fucky weird thing where it turns from a 2 electron transfer to a 1 electron transfer. So the QH2 goes through steps, right? Which eventually turn into Q radical anion, right? But the oxidation happens through what? Cytochrome C ox turns into cytochrome C reduced, right? And then the Q radical anion comes back, picks up another electron from a Q radical anion, makes another QH2, QH2 turns into blah, blah, blah. Eventually, this is going to turn back into Q and disperse out there. Do you need to know the specifics of that? Not necessarily. Will it help you if you do? Of course. But I feel like this is enough to know that there's an intermediate, which is a radical anion, right? And because 1 electron got taken off, and the fact that that radical anion is eventually going to circle back, reform Q, and the Q is going to go back and do that whole thing over again. What's the point of switching to a 1 electron transfer? Why did we? Oxygen can only do what? 1 electron at a time. Oxygen only accepts electrons 1 electron at a time because he's a picky bitch who doesn't care what anyone else wants. As you can see, I have a lot of hatred for oxygen. I'm just going to stop breathing. Yes?
What's that third complex called?
This? What's it called? It's just like Q cytochrome C oxidoreductase. This is just succinate dehydrogenase. Most people say complex 2 is kind of succinate dehydrogenase. Or you can say FADH2Q oxidoreductase. Complex 4 is the one with the interesting name. All right, also complex 3, pumps. Right? So we're building up this proton motive force inside of the intermembrane space, right? Complex 4 is called what? Cytochrome C oxidase, right? Because it's not going to be called cytochrome C oxygen oxidoreductase. Oxygen's just oxidizing cytochrome C, right? It's stealing the electrons, right? Oxygen's taking your girl. So here's cytochrome C, R, O2, whatever O2 turns into, it combines with hydrogens, whatever. It probably turns into like superoxide, or it turns into like, peroxide, or whatever it is, right? And this is cytochrome C, ox, and it goes back here. Everything's a cycle, right? And then that O2 is also gonna pump, and then eventually, when you have ATP synthase, which is the big fan, the big generator, right? You're gonna start pumping out ATP from free phosphate and ADP, and it's going to be linked, it's going to be channel linked to the H plus that moves down its concentration gradient in order to spin the fan, right? And when that H plus comes down, it's able to link up with this oxygen and make water. And this is called ATP synthase, or complex 5. For nerds, right? Now, why is it not called ATP synthetase? Why is it called ATP synthase? Because a synthetase uses a nucleotide, right? So succinyl-CoA synthetase makes GTP. There's a GTP involved, right? A synthetase will involve a nucleotide or nucleoside triphosphate, right? Synthase means there's no use of energy. Was that a good overview of your electron transport chain? Yeah? Yeah.
So with oxygen, what's happening?
It is oxidizing the cytochrome C, stealing its electrons, and combining with hydrogens to make water.
What's the fourth complex called?
Cytochrome C oxidase.
Could you explain? I remember you talked early on, at the very beginning of lecture,
So basically, there's like, it's a huge molecule, right? And it's a big aromatic ring, whatever. And there's a whole reduction that takes place, and there's a free hydrogen that kind of tacks onto it and travels with it. Yeah. You all right? Anyone else? Yeah? That's the electron transport chain. The iron thing, yeah. They're just iron sulfur cores. Like, they're like intermediates between the things. So basically, like, you're reducing the iron down. So Fe2 plus can turn to Fe, Fe2 plus Fe, Fe2 plus, or like Fe3 plus Fe, whatever. Like, the reduction and the electrons get transferred all the way up there, and then they end up on Q. You don't need to know the specifics of that. I'm sure there's some biochemist who gets like really, really horny for the iron sulfur cores.
And that's in complex 1.
Complex 1 and 2, yes. When I was like a noob, like an MCAT noob, I used to get cytochrome C and coenzyme A mixed up in my head. And then that was not a mix-up you want to make. Okay? Yeah? So this is where all that ATP comes from. And this is also what's messing with your ATP to ADP ratio, right? So more ADP inside of ATP synthase that's not making it is going to decrease the ATP to ADP ratio, right? Because there's more ADP. That's going to push glycolysis forward and also activate the TCA cycle. The increase in ATP from here is going to be transported out of the mitochondria, increase the ATP to ADP ratio of the cell, mitochondria, everything like that, right? And that increase in the ATP to ADP ratio is going to negatively or inhibit PFK1, isocitrate dehydrogenase, all those sort of pro-energy effectors, right? My eyes are on fire. Thank you guys so much for coming to Biochem Rapid Review. There will be more parts to this. Trust me, there's a lot more to learn in Biochem. I'll see you next time.